This is lesson 15 of our Calculus 3 series, Tangent Planes and Linear Approximations. In this lesson we're going to talk about tangent planes and linear approximations, but let's go back to what we learned in Calc 1 about tangent lines and linear approximations to functions of one variable. So let's recall that for y equals f of x, the tangent line to f of x at x equals x naught is y minus f of x naught is equal to f prime of x naught times x minus x naught. Right? This is y minus y naught equals m x minus x naught. So our slope m is the derivative of the function at that point, because the slope of the tangent line at that point is the same as the slope of the function at that point. And we have to plug in the point of tangency x naught y naught, or x naught f of x naught. So this is our equation to the tangent line. And then if we just move the f of x naught over to the right-hand side, we get y equals f prime of x naught times x minus x naught plus f of x naught. And this gives us a linear approximation of f of x near x equals x naught. So we said the slope of the tangent line is equal to the slope of the function at that point, and we can use the tangent line to approximate function values for x values that are near x naught. So we're using this equation of the tangent line to approximate f of x for x values that are near x naught. And then we'll call this right-hand side the local linearization of f at x naught. And we'll just take a look at an example before we get into functions of two variables. So for example, f of x equals 8 minus x squared. We want to take a look at the tangent line at x equal 1. So we take f prime of x, that's negative 2x. We plug in this x value, and so f prime of 1 is equal to negative 2 times 1, which is negative 2. We also know that f of 1, the y value that goes with x equal 1, is 8 minus 1 squared, so that's 7. So the equation of the tangent line looks like y minus 7 is equal to negative 2 times x minus 1. And solving for y, we're here. Normally we go on to simplify a little bit further, but for the linear approximations it's actually nice to keep it in this form. So if we wanted to approximate, for example, f of 1.1, we could plug 1.1 into this tangent line function. And that would give us an approximation to the function's value at that point. So we plug 1.1 in for x, and we get 6.8. And by plugging 1.1 into the actual function, we can see that we should have 6.79. So we got a close approximation. And let's take a look at what this looks like graphically. Here's a parabola y equals 8 minus x squared. Here's the point where x is equal to 1. That's the point of tangency. That's our tangent line. Now zooming in there and looking at what's happening at x equals 1.1, notice the difference between the original function and the tangent line. What we found is that by using the linear approximation or the tangent line approximation, we found the y value is 6.8. The y value is 6.8. That's the value on the red line here. The actual value of the function is on the gray curve here, and that's the 6.79 that we computed. So we're using the tangent line as an approximation to the original function, just to simplify things, because linear computations are going to be the simplest kind of computations that we can make, and generally that's simpler than the functions that were given. So we can use a linear approximation to make easy computations to approximate our function values. Now let's take a look at what's happening for z equals f of xy. Instead of a tangent line, we're going to have a tangent plane at x naught, y naught, z naught. And we can use the equation of the tangent plane to approximate function values for xy near x naught, y naught. Now what's the equation of this tangent plane going to look like? Well, we know the equation of any plane is a x minus x naught plus b y minus y naught plus c z minus z naught, where x naught, y naught, z naught is a point on the plane and abc is a normal vector to the plane. Now here we're given a point, it's the point of tangency, so it's x naught, y naught, z naught, or we could say x naught, y naught, f of x naught, y naught. How do we find a normal vector to this plane? Based on the partial derivatives, fx and fy at the point x naught, y naught, we'll find two vectors in the plane, and their cross product will then be a normal vector to the plane that we can use for our equation. Here we have a surface, we have a paraboloid, and a tangent plane to the point x0, y0, z0. Or we can say a tangent plane at x0, y0. Now how are we going to find vectors in this tangent plane? Well, if it's a tangent plane and we restrict our attention to what's happening in the x direction, so if we fix y at y equals y0 and we look at what's happening in the x direction, we know that the tangent vector to this curve at this point must be in our tangent plane. Right? This is the curve of intersection between y equals y0 and the surface. And the tangent vector to this curve at this point must be in our tangent plane. Well, what's that tangent vector? We know that the slope of this curve at this point is given by the x partial derivative at x0, y0. So let's use that slope to determine a tangent vector to the curve at that point. We know the slope in this direction is given by the x partial at x0, y0. So let's think about what a tangent vector to this curve would look like at this point. We know that the x partial gives us the change in z with respect to a change in x. So this means if we had a 1 unit change in x, we would expect the change in z to be given by the x partial. If we had a 1 unit change in x, the change in z would be given by the x partial. Well, what's the change in y for this vector? There's no change in y since we're along the plane y equals y0. So this tangent vector to the curve must be in the tangent plane. Similarly, if we fix the x direction and look at the change in the y direction, we can talk about the slope in the y direction, which is given by the y partial. We know that gives us the change in z with respect to a change in y. So if, for instance, we have a 1 unit change in y, then we would expect the change in z to be given by the y partial. And in this case, in this vector, there's no change in x because we're along the plane x equals x0. This is another tangent vector that must be in the tangent plane. So now we have two vectors that are in our tangent plane. So how do we get a normal vector to the plane? We take their cross product. Taking their cross product leaves us here. And this gives us the ABC, the normal vector to the plane. So now we can go back to our equation of the plane and fill in all of our details. We're at the point x0, y0, z0, or x0, y0, f of x0, y0. And our normal vector looks like this. So here's our equation of the tangent plane to z equals f of x, y at the point x0, y0. And if we solve for z, it looks like this. So now, similar to what we did in functions of one variable, we could use this tangent plane to approximate function values for x, y points that are near x0, y0. So we could say f of x, y is approximately equal to what we get from the tangent plane for xy near x0, y0. And this is again our linear approximation. And if we call this right-hand side L of xy, we call that the local linearization of f at x0, y0. And notice that our normal vector to the tangent plane is also normal to the surface at this point. So we could talk about having a normal line to the surface at this point. And so that normal line would have that normal vector as its direction vector, and it would go through the same point, x naught, y naught, z naught. So let's take a look at an example. F of xy equals 8 minus x squared minus y squared. This is actually the equation of the surface that we were just looking at in the graphics above. Find the equations for the tangent plane and normal line through the point 1, 2, 3. So now this point 1, 2, 3, this is our x naught, y naught, z naught here. And if we're looking for equations for the tangent plane, we know that we're going to need the x partial and y partial for the a and the b of the normal vector to this tangent plane. So we compute our x and y partials, and we plug in the 1 and the 2 that were given as x naught and y naught, and we get our x partial is -2 and our y partial is -4. So then the equation of our tangent plane looks like this. And we're also asked for the equations of the normal line. We're taking that same vector, -2, -4, and -1, and using that as a direction vector with the same point, 1, 2, 3. So let's see what that looks like. And here we see our tangent plane and the normal line through the surface at that point. And we can use the equation of this tangent plane to approximate function values for x, y points that are near the point we were given, which was 1, 2. So our local linearization looks like this, solving for z, and we can plug in our x and y values, and we get 2.2 as the approximate function value. So 2.2 is the z value that you get on the tangent plane above the point 1.2, 2.1. And just to compare it to the actual value, by plugging it into the original function, we get 2.15. So that's a reasonable approximation there. And to view that graphically, this top point here is what we got by using the tangent plane as an approximation to the function, and the bottom point here is the z value that goes with the actual function. So that's our tangent plane and our surface zoomed in near x value of 1.2 and y value of 2.1. Now let's take a look at tangent planes to parametric surfaces. Recall from lesson 10 that a parametric surface is defined by x is a function of u and v, y is a function of u and v, and z is a function of u and v. And for example, we saw the paraboloid z equals x squared plus y squared written as x equals v sine u, y equals v cosine u, and z equals v squared. So this parametric representation described this paraboloid. Now consider the position vector function for this parametric surface. We have r of uv as x of uvi plus y of uvj plus z of uvk. So this vector function r is giving us a vector from the origin to the point on the surface at coordinates uv. So for example, our position vector function will look like v sine u I plus v cosine u j plus v squared k. And so to find a tangent plane at a particular point, say u naught v naught, or say pi over 4 3/2 in our example, we want to consider the curves obtained by holding each variable constant. So for example, if we're at the point on our paraboloid defined by the point u equals pi over 4 and v equals 3/2, we want to take a look at r of pi over 4 comma v and r of u comma 3/2, because these are going to be curves along our paraboloid. So r of pi over 4 comma v, notice this is a curve in three-dimensional space. It has only one parameter v. Similarly, this is a curve in three-dimensional space using only one parameter u. So those are these curves along the paraboloid. So this is r of pi over 4v, and this is r of u 3/2. Now we know how to find tangent vectors to curves in three-dimensional space by looking at the derivative of each of the component functions. So if we take the derivative of r of pi over 4v, we're going to get a tangent vector to this curve at this point. And if we take a look at the derivative with respect to u of these component functions, we're going to get a tangent vector to this curve r of u, comma 3/2. So generally speaking, this is how we find our tangent vectors to the surface. And in our example, we're here. And so these are the tangent vectors that we have, given by r sub v and r sub u. Now we know that these vectors are tangent to their corresponding curves, but that also means they're tangent to the surface. So we could take their cross product and get a normal vector to the surface, which would serve as a normal vector for our tangent plane. So we take the cross product, and we're here. So what we have found here is a vector that is normal to our surface, and therefore also normal to the tangent plane to the surface at that point. Now for our particular example, this normal vector is pointing inward into our paraboloid, and just to get a nice visual, I chose to negate the vector so we can take a look at the outward pointing normal vector. So I just negated each component, and now this becomes a little bit more clear to visualize. And remember that for our tangent plane, we need the point of tangency, so the point on the surface, and any normal vector to the surface at that point. Now when I look at this normal vector, I realize there are denominators, and I figure why not scale by a factor of 4 to get rid of my denominators. Remember that you just need any normal vector at that point. So any vector parallel to this would work. So I multiplied by a factor of 4, and now I'm going to use this in my tangent plane. So this is going to be our normal vector, so this is going to be A, B, and C. That's here. And the point on our surface is defined by u equals pi over 4 and v equals 3/2, so we plug that into the original parametrization, and we get 3 radical 2 over 4, 3 radical 2 over 4, 9/4 as the coordinates of the point on the surface. And so those are the x0, y0, z0 values. And so we plug into our tangent plane equation, and we're here. And so this is how we find tangent planes to parametric surfaces. Now let's talk about increments and differentials. Recall from Calc 1 that for y equals f of x with f differentiable, we can talk about the differential dx and the differential dy. The differential dx is an independent variable, meaning it can take any value, and then from that we define the differential dy to be f prime of x times dx. So for example, with f of x equals 8 minus x squared as we had above, we can take a look at the graphical understanding of the differentials. So we're saying that dx could take any value, and in fact we're treating that as a difference in x values. So if we're talking about originally the tangent line at x equals 1, we move over some amount in x and we'll call that dx, and now we're taking a look at dy, which is f prime of x dx. So this is saying take the amount that you moved over and multiply it by the slope at that point of tangency. Where does that leave us? Well, that leaves us further down the tangent line. So dy is the change in y from moving along the tangent line to the function at that point. So we could think of dy as a change in y, but it's the change in y along the tangent line. Compare that to delta y, which is the change in y along the function. And when we do the comparison, we talk about delta x, but we make delta x equal to dx, just to understand the comparison there. So again, delta x or dx is going to be the change in x that you're moving over, and then the differential dy tells you the change in y as you move along the tangent line, whereas delta y tells you the change in y from moving along the original function. And delta y is then called the increment in y. And we're saying that's the change that we get from using the original function, so that's f of x plus delta x minus f of x. The change in y is the new y value minus the old y value. And in the notation of differentials then, the linearization or the tangent line approximation that we talked about for the function of one variable will look like this. With dy, replacing f prime of x, x minus x naught. So our approximation of f at the new x value, given by the linearization, is the old y value plus the change in y by moving along the tangent line. Now, to talk about differentials with functions of two variables, we have to recognize something important first. Note that the idea of using a linear approximation in differentials relies on f being differentiable at and near x naught. That means f prime exists at and near x naught. Now, to be able to talk about linear approximations with functions of two variables, we need a definition of differentiability that's more than just having our partials exist, because we could have functions where the partial derivatives exist, but the tangent plane does not give a good approximation. And so we're going to look at what it means to be differentiable for a function of two variables. But first we're going to need some notation. Just like we talked about the increment delta y in functions of one variable, we're going to have the increment delta z with functions of two variable. So if we take delta x and delta y to be independent changes in x and y, so we're going from the point x comma y to the point x plus delta x comma y plus delta y, then delta z, the increment, is going to be the difference in the corresponding z values. So if this is xy, and we have a delta x change in x, and we have a delta y change in y, this is our new point x plus delta x, y plus delta y, and taking a look at its function value as compared to the original point's function value, the difference between the two is delta z. And so our definition of differentiability is going to look like this. For z equals f of xy, f is differentiable at x naught, y naught if delta z can be expressed in this form. Now notice this looks very similar to the equation of the tangent plane. We have the x partial at x naught, y naught, and delta x is x minus x naught. We have the y partial at x naught, y naught, and this is y minus y naught. And our tangent plane has z minus z naught. We're defining differentiability this way so that we can ensure that the difference between the z values on our original function and on our tangent plane are going to be going to 0 as the difference in x and y goes to 0. And the nice thing about this definition is that if our partial derivatives exist near x naught, y naught and are continuous at that point, then f is differentiable. So if we're asked to show that a function is differentiable, we're not going to show this definition holds. What we're going to show is that our partial derivatives exist near our point and are continuous at that point. That gives us the differentiability that we need. And that allows us to use the tangent plane as a linear approximation to the original function. Now in terms of differentials, with that notation, we have dx and dy are independent variables, meaning they can take on any value, and those are independent changes in x and in y. Then our total differential looks like this. dz is equal to the x partial times dx plus the y partial times dy. And so our local linearization, which we know looks like this, can be written in terms of differentials z naught plus dz, or f of x naught, y naught plus dz, the total differential. Now let's take a look at what the total differential gives us graphically speaking. Here's our point in the domain x naught, y naught, and here are dx and dy, the independent changes in the x and y directions. So the new point that we have is x naught plus dx, y naught plus dy. If we take a look at the point on the surface for x naught, y naught, we're here, that's this blue point here, x naught, y naught, f of x naught, y naught. That's also the point at which we're taking the tangent plane. And let's take a look at our total differential dz. It's defined to be f sub x at x naught, y naught times dx plus f sub y at x naught, y naught times dy. Let's take a look at the first term. We're taking the slope in the x direction and we're multiplying that by the distance we're moving in the x direction. So we're taking the slope in the x direction at this point and multiplying that by the distance we're moving in the x direction. That's going to give us this purple distance here. That's a change in the z values. Similarly, if we start at our original point and we look at the y partial and multiply that slope by the distance we're moving in the y direction, we're going to get this green distance here, the change in z. Now we're looking to combine those two distances because we're looking at the total differential. We want to consider the slope in the x direction multiplied by our change in x plus the slope in the y direction multiplied by our change in y. So we need to combine these two distances. So what we're doing is we're starting at this original point, and we could think about moving in the x direction along the tangent plane. That brings us here to this purple point on the tangent plane, and then from there moving in the y direction along the tangent plane, and that brings us to our resulting red point here. And so what we're doing is combining the changes in z, the purple distance and then the green distance, which is written here. And so from the blue point to the red point, our total change in z is given by the purple distance plus the green distance, and that can be seen here as well. The total difference we have in z is our total differential, dz. So changing in the x direction results in a change of z values. Also changing in the y direction results in a change of z values. And we're moving in both directions, x and y, so we're combining the changes in z values. And so dz, our total differential, is the sum of those changes in z. And so the value we get from our local linearization is then the original z value plus the change in z along the tangent plane. Now let's take a look at an example. Let's use differentials to find an approximation to the cube root of 2.02 squared plus 3.97. So if we're going to be using differentials, then we're going to need a function f of xy. We're also going to need a point of tangency, right? Where are we taking this linear approximation? So the function looks like we have one value squared here and a different value added in. So this should be cube root of x squared plus y. And the 2.02 is very close to 2. The 3.97 is very close to 4. So these are going to be convenient values for us at which to take the linearization. Remember that the linear approximation only holds for x and y values that are near the original point. So if this is our original point, we have to make sure that the values we're looking for are close to it. So we've got 2 and 4 here. Now, in case you might be wondering, if you wanted to have y squared plus x, that's perfectly okay. You're just going to have y is equal to 2 and x is equal to 4. So you'd have these switched. Your end result will come out the same. With what we have here, our approximation is going to be given by f of 2, 4 plus dz, the total differential. Plugging in 2, 4 to our function gives us cube root of 2 squared plus 4, so that's cube root of 8, plus we have the x partial at 2, 4 times dx plus the y partial at 2, 4 times dy. So we need these x and y partials. So let's make those computations. Our x and y partials look like this. And plugging in the point 2, 4, we get our x partial is 1/3 and our y partial is 1/12. So that going back to our linearization, we have 2 plus 1/3 times 0.02, that's 2.02 minus 2, plus 1/12 times dy, which is 3.97 minus 4. And so that gives us 2.00417. And plugging in these values to the actual function would have given us 2.00419. So got a very close approximation. Now, what happens if we have more variables in our function? Well, more variables in our function are going to give us more terms in our linear approximation. So for example, a function of 3 variables would have linearization that looks like this. So let's find the linear approximation to f of x, y, z is equal to ln of x plus 2y minus z at the point 0, 1, 1. And let's use it to approximate f of 0.1, 0.9, 1.2. Now notice 0.1 is near 0, 0.9 is near 1, 1.2 is near 1. Right? These values need to be close to the original values. Otherwise, the approximation wouldn't be valid. So we take our x, y, and z partials and we plug in 0, 1, 1. We get 1, 2, and negative 1. And plug that into our linearization. So that our local linearization looks like x plus 2y minus z minus 1. And then we plug in the values that we wish to approximate at, and we get a negative 0.3. And just to compare, if we plug in the actual values, ln of 0.1 plus 2 times 0.9 minus 1.2 gives us negative 0.357. So we have a reasonable approximation there. And we'll conclude our lesson on tangent planes and linear approximations here.